Hey everybody, welcome to another lecture of Nets 412. I'm gonna quickly unmute you all so we can all say hi. Hey everybody.
Hey.
Hi.
All right. So today I want to talk some more about revenue maximization and profit maximization. But I want to start what will be a series of lectures thinking about how we should go about doing this when we have only limited information. So we studied revenue optimality in a couple of settings. We studied Meyerson's optimal auction when we want to maximize revenue and we have all of the bidders up front. And we studied competitive pricings when we can't aggregate all of the bidders up front, but we still want to obtain revenue that is competitive with the revenue of the revenue optimal auction. But in both of these settings, we assumed, crucially, that we knew the distribution from which bidder valuations were drawn, right? We assumed that we knew that there was some distribution D, and we assumed that everyone's valuations were drawn independently from this distribution. And this was important for two reasons. It was important, first, because we used it explicitly in the design of our mechanisms, right? Like in the revenue optimal auctions, we needed to know D in order to set the reserve prices. And in the pricing scheme, well, we needed to know quite a bit about D in order to figure out what the optimal prices were. And that's kind of a bummer because, you know, how are we going to know this distribution D, right? Like, you know, you can set up an auction, but when it comes down to, you know, like writing down in your particular setting to sell widgets, what is the virtual value function, you'll probably be at a loss, right? Like, how are you going to figure out what D is? And, you know, up until this point, up until when we talked about revenue, we didn't need to make any kind of modeling assumptions of this sort. And, you know, these are really unrealistic modeling assumptions. It's nice when we're doing derivations to pretend that we know what this distribution D is, but really we're not going to have, you know, sufficiently fine-grained information about our market to be able to write down what this distribution is, even if we believe that ultimately, like, there is some distribution. And when we derived the VCG mechanism, for example, when we were talking about welfare maximization, that wasn't a problem, right? The VCG mechanism is able to, without any knowledge of where people's valuations come from, it's able to maximize welfare because it does so on a case-by-case basis, instance by instance. And so the question that I want to ask in this class is it sensible to think about revenue in a distribution independent way? And let's just remember the two ways in which it was useful for us to assume that we had this distribution D. I mean, first, it was explicitly used in the design of our mechanisms. But more fundamentally, we used this distribution even to define what we meant by revenue optimality, to define our benchmark. And so, in addition to designing new algorithms, new mechanisms, we're going to have to think carefully about what revenue maximization means if we don't have a distribution, and what our benchmark should be. Okay. So you can think about this in a wide variety of settings. What I'm gonna do this lecture is go through the exercise of trying to think about revenue in a distribution-free setting. In a particular case, a particular setting called digital goods auctions, which are especially simple. And so we'll think about it in this setting. Okay, and what is a digital goods auction? You know, you could alternately call it an unlimited supply auction. And the idea is that it's modeling the sale of goods that have zero marginal cost of production. So the reason these are called digital goods auctions is because you should imagine maybe that the thing that you're selling is a copy of a piece of software. Like maybe you're selling, you know, a copy of Windows 95 or Microsoft Word. And the point is, you know, even though it might have cost you a great deal to develop the first copy of Microsoft Word. Once you've done it, once you've coded up Microsoft Word, you have no additional marginal cost for selling it to an additional person. So there's no artificial supply constraint here. It's not like I'm selling toilet paper and I only have 2 rolls of toilet paper, so there can only be 2 winners. If I'm selling copies of Microsoft Word, I can make copies of it for free. And if I'm running an auction, say, there can be as many winners as I want. Okay, so this is just going to be some auction setting in which there's no constraint on how many individuals can win the auction because there's no supply constraint. So formally, a digital goods auction is a pretty simple thing. It's a single parameter domain, first of all. And the set of feasible alternatives are just the set of all subsets of bidders. Okay, so an outcome, an alternative that my mechanism is going to choose is just some subset of the bidders, and we'll interpret those as the bidders who win the auction. They're the ones who are going to get to download a copy of Microsoft Word. And there's no supply constraints, and so the way that manifests itself is that all subsets of bidders, including all of them, are feasible alternatives, right? I'm not limited to declare only 1 or only 2 winners. And so we can, again, use this sort of indicator notation to talk about alternatives, where I'll think of the alternative A as being a vector of length n, and the index AI corresponding to bidder I is just going to encode the outcome relevant to bidder I, which is, did bidder I win the auction? So AI is going to be 1 if bidder I was one of the winners of the auction, and it's going to be 0 otherwise. And this is a single parameter domain. And so, all that means is that we know ahead of time that everyone would prefer winning the auction to losing the auction. The only thing that's unknown is their valuation VI, and their valuation function is just vi.ai. It's VI if they win the auction and 0 otherwise. Okay. And digital goods auctions are sort of a good case study for thinking about profit maximization, revenue maximization, because it's clear that welfare maximization and profit maximization are in conflict here, right? Because there's no supply constraint, if I just wanted to maximize welfare, maximize the sum happiness across society, I would just give the good to everybody. I would declare everybody to be a winner, right? Because that's, only a win for me. It doesn't make anyone else less happy to give Sally a copy of Microsoft Word, and it makes Sally happier. And so no matter what the instance is, the welfare maximizing solution corresponds to declaring everyone to be a winner. But of course, if we do that, then the only payment rule that's going to make reporting your valuation a dominant strategy is to charge nothing, right? If everybody's going to be a winner, I can't charge you anything, because to incentivize you to report truthfully, what I have to do in these kinds of auctions, as we've seen a number of times, is charge you the smallest bid that you could have made and still won. That's why in a single item auction, I have to charge you the second highest bid. That's the threshold at which, if you bid above that, you would become the winner. And if my allocation rule is to give everybody, no matter what their reported valuation, the item, then no matter what bid you put in, so long as it's not negative, you would be a winner. And so the price that I would have to charge you to get dominant strategy incentive compatibility would be 0. And that's exactly what the VCG mechanism would do, right? It's easy to maximize welfare in this setting, but maximizing welfare in this setting would correspond to not making any money at all. And so because of that, if we want to make money, if we want to maximize revenue, we need to artificially limit supply, right? Like we could maximize welfare by making 8 billion copies of Microsoft Word and giving it to everybody, but that's not what we do. That's not what Microsoft does, because they want to make money. And they need to come up with a solution that doesn't give the item to everybody if we're going to be able to charge them anything at all. And so the solution is going to have to involve artificially limiting supply. But before we talk about the solution, like how we can go about being competitive with the optimal revenue mechanism, we have to think about what we even mean by optimal revenue, right? So when we talked about this before, we were in this sort of stylized setting in which there was some prior distribution from which bidder valuations were drawn, right? And not only did we use that in designing our mechanisms, we used that in designing our benchmark, right? So we said, okay, like for any truthful mechanism, I can talk about its expected revenue in expectation where the buyer's valuations are drawn from this distribution. And once we had that down, it made sense with respect to a particular distribution to talk about the mechanism that had the highest expected revenue. But it doesn't even make sense to talk about that. It doesn't even make sense to talk about that if we don't have a distribution, right? And so, we mentioned the problem of benchmarks a little bit a couple of classes ago when we introduced why it would be convenient to think about these distributions. But the problem was basically that if I want a worst case notion of revenue, well, there's always some truthful mechanism that happens to make really a lot of revenue, like on any particular instance. It's the mechanism that has for each bidder a hard-coded price that they're going to be charged, just a constant price. So it's a truthful mechanism. But it's the mechanism for which those hard-coded prices happen to be exactly the values of the bidders. And so the revenue, there's always a truthful mechanism that on any particular instance extracts full revenue. It gets everyone to pay exactly their valuation. Of course, that's not a fair comparison because I would have no way of knowing people's valuations ahead of time. And so although, on any particular instance, there's a truthful mechanism that does well, those particular truthful mechanisms would not do well on other instances. So, okay, so what's a reasonable benchmark? Not that one. But here's one way to think about it. So we're going to really be thinking about a worst case setting here, where the valuations, not only do we not know the distribution from which valuations are drawn, we're not even going to assume that the valuations are drawn from a distribution. We're going to want to give guarantees that hold in the worst case for every vector of valuations we might have gotten. But still, we can think about how we can, what a sensible benchmark is by imagining what would happen had the bidder valuations been drawn from a distribution, and it just so happens that we didn't know that distribution. So had bidder valuations been drawn from a distribution, we know what the revenue optimal auction would look like, right? We would not know the specifics unless we knew the distribution, but because this is a single parameter domain, we know that, well, for the distribution, there would be a virtual valuation function phi, and the revenue optimal auction would give the item exactly to those bidders whose virtual valuation was positive, or at least was non-negative. Okay, and this would correspond to setting a fixed price, P, equal to the inverse of this virtual valuation function evaluated at 0. That's the cutoff at which the virtual values go from being negative to positive, and therefore that's the cutoff, that's the sort of the minimum amount you would have to bid in order to win the item. And so that's the price we would charge in a truthful auction. So, we don't know what this price is, right? Because we don't know what this virtual valuation function is, because we don't know what the distribution is. In fact, we don't even know that the valuations were drawn from a distribution. But suppose we could say that we get revenue that is competitive with the revenue that we could obtain on this instance using the best fixed price. That is, we will consider all fixed prices we could set from 0 to infinity. On our instance, there will be some fixed price that achieves the best revenue. Every fixed price achieves some revenue. There'll be some fixed price that achieves the best revenue. if we could say that the revenue our mechanism obtains instance by instance is competitive with the revenue of the best fixed price on our instance, that would be pretty good. Because what that would mean in particular is that if it turned out that our bidder valuations really were drawn from a distribution, even though we didn't know what that distribution meant, that we would be competitive with the revenue optimal auction that had knowledge of the distribution. Because we know that whatever that auction is, it corresponds to setting some fixed price. Okay, so if we can be competitive with the best fixed price on our instance, that in particular means that we are competitive with an entire class of auctions that contains revenue optimal auctions for every distribution D. Okay, does that make sense? So we don't have a distribution on which we can define a revenue benchmark, but it makes sense to evaluate the revenue that's obtainable by any particular fixed price on our instance. And because we know that optimal auctions with knowledge of a distribution would correspond to fixed pricings in this setting, if we can be competitive with fixed pricings, that's only stronger. That's only a stronger guarantee than being competitive with the optimal auction that gets to know the distribution, even though we as the mechanism designers don't know the distribution. And so we're going to try to think about whether we can achieve that. And so let's think about fixed price benchmarks, because they have a little bit of structure that's going to be useful for us. So first of all, right, I can set my price to be whatever I want. So I can set my price to be, any number between 0 and infinity. Looks like I've got a question. When we say we don't know that the valuations are drawn from a distribution, even an unknown one, what does that actually mean? Would that imply that the valuations themselves could be based on the prices the buyers see? How else could they not be based on some distribution? So the claim, or what we're going to do is we're going to give a guarantee that is sort of the same form as the VCG mechanism, in that it will be instance by instance. We're saying for every like the theorem we're going to prove at the end will have the following form. It'll say for every possible vector of valuations, we are going to achieve revenue that is some multiple of the revenue that would have been obtainable by using the best fixed price in hindsight on this instance. So it's sort of an instance by instance guarantee, like the welfare guarantee of the VCG mechanism, and unlike these sort of Bayesian guarantees that are in expectation. So in particular, like when we derived the revenue optimal auctions in these Bayesian settings, we used structure, like the fact that the valuation functions were drawn independently of one another. So none of that's here. Like we're going to prove a theorem that's going to have to hold even if the vector of valuations is chosen in some, like adversarial way by an adversary who's trying to get us to not make any money, as opposed to assuming that there's some nice structure that, for example, valuations are drawn independently of one another, or that I can get information about the distribution from, person A's valuation that is, informative about what person B's valuation is. Does that make sense? But really the point is we're going to aim to give an instance by instance guarantee, because it no longer makes sense even to talk about average case guarantees. There's nothing to average over. Great. Okay. So let's think about the structure of fixed prices. How much money can we make at fixed prices? Okay, so we can set any possible price from 0 to infinity. And on any particular instance, right, on any particular set of n buyers valuations, we can think about how much money we would make at that fixed price. In particular, if I say, Microsoft Word costs $P, then who am I going to sell to? Well, I'm going to sell to exactly those people who value Microsoft Word at more than $P. And each of them will pay me the price, P. And so the amount of money that I will make is exactly P, that's the amount of money I make per sale, times the number of bidders whose valuation is bigger than P. That's the number of people who find it worthwhile to pay me $P. And here's an observation and a question. So I claim that even though in principle, the price that I could pick, the best fixed price in hindsight, could be any number between 0 and infinity, I claim that actually, if you're asking me on this data set, on this particular set of n buyers, what's the price that makes me the most money? It's always going to be equal to one of the buyer valuations. The best price that I can charge is going to be equal to the valuations of one of the n bidders. And can anyone tell me why this is? How come without loss of generality, I can always restrict attention to prices that are equal to people's valuations? Someone is bravely trying to answer the question with their microphone. Yes, we have an answer in the chat. We always do better by rounding to the nearest valuation in the set. That's right. So let's think about this, right? Like, suppose I were to set some price that was in between two valuations, in between V1 and V2, say. So what happens if I raise the price a little bit, right? Like, because what's my profit? It's the price times the number of people whose valuations are at least as high as the price. So if my price is strictly between two valuations, that means I can bump the price up a little bit, just a little bit, without it exceeding anyone's valuation, right? Like if my price wasn't exactly equal to the valuation of the first buyer whose valuation was higher than the price, then there's a little bit of room for me to wiggle the price upwards without exceeding that person's valuation. And so I can wiggle the price upwards without changing the number of people who are willing to buy at that price, but increasing a little bit how much each of the people who are willing to buy pays. Right? So that means that a price that is not exactly equal to some person's valuation cannot possibly be the best fixed price in hindsight, because I could wiggle it up just a little bit and make just a little bit of money. And so the conclusion we can draw from that is that, if I'm just looking at the best fixed price in hindsight, like, of course, this doesn't make sense in an average case setting because I don't know what the valuations are ahead of time, and I can't set my price equal to one of the valuations in a dominant strategy truthful way. But if I'm just looking in hindsight, given a vector of valuations, what is the number P that maximizes P times the number of people whose valuation is bigger than P? That has to be, the P has to be exactly equal to one of the valuations. Okay. And so that means that I can write down this revenue benchmark of the best fixed price in hindsight in a pretty simple way. And we'll write it as opt, right? For the optimal revenue achievable by any fixed price on a particular instance V, a particular vector of valuations. And it's just going to be the maximum. Now, instead of taking the maximum over all of the continuously many prices, I'm just taking the maximum over the n bidders. It's the maximum over all bidders I of the valuation of bidder I times the number of bidders whose valuation is higher than that of bidder I. And I can write that even more concisely by introducing this notation V sub I to mean the valuation of the ith highest bidder in sorted order. And so the optimal revenue achievable by any fixed price, I can write as just the maximum over all indices I between 1 and n of I times the value of the ith highest bidder. Okay, the reason I can write it this way is because of this observation that the best fixed price in hindsight is always exactly equal to one of the bidders' valuations. Okay, so that's our benchmark, or that's a benchmark. But even this benchmark, if you think about it, it's actually like for sort of a corner case, still not achievable. Like we can't even approximate this benchmark with any dominant strategy truthful mechanism. And the problematic case is when I equal to 1 in this maximization, when the best fixed price in hindsight ends up selling to only one person, right? So suppose I'm selling a roll of toilet paper, and I'm selling. I have a toilet paper factory. I've got lots of toilet paper, and I'm just figuring out how to price it. And I'm computing, like the revenue of each fixed price. Well, like the bad case for this benchmark is where most of you have a good supply of toilet paper, so your valuation for this thing is, like 50 cents. But one of you has been out of toilet paper for a week, you're in desperate need of toilet paper, and your valuation might be, I don't know, $1,000. You've got a fancy event coming up and you really need to clean up. So the problem is that in that case, it might be that the maximum revenue is achieved by setting the price to be $1,000 and selling to only one person, selling only to the high bidder, right? So the problem is, this can be, there's sort of this like edge case where like, I've got like, it's a digital goods auction, so the expectation is that I'm going to sell to many people. But in principle, like the maximum revenue could be obtainable by selling to only one person and setting the price equal to their valuation. And the problem is we can't do anything like that in a truthful way. And just to sort of convince yourself of that, consider the case in which there really only is one bidder. Right? If there's only one bidder, then this benchmark is going to be exactly equal to that bidder's valuation. So if you're the only person in the market and your valuation is, 50 cents, then the benchmark is 50 cents. If your valuation is $1,000, the benchmark's $1,000. And I just cannot, in a dominant strategy truthful way, set the price as a function of your valuation, right? Because if there are, two possible bids you can make, both of which will cause you to win the item, but will force you to pay different prices, of course, you're going to report the valuation that causes you to pay the lower price, even if that's not the truth, right? And so the price that you have to pay in a truthful mechanism had better be independent of your report if you win the item. And if that's the case, then I cannot compete with this benchmark in the case in which there's like only one bidder, because this benchmark is just the valuation of that bidder. So we're going to need to like tweak the benchmark a little bit in a way that will sort of eliminate this corner case. And so here's like the benchmark, the only very slightly weaker benchmark that we will in fact be able to compete with. And it's the revenue of the best fixed price, with the slight caveat that at this best fixed price, we have to sell to at least two people. So it's just sort of cutting out this like little corner case where like maybe the best fixed price was going to sell to just one person and therefore have to charge that person exactly their valuation. Okay, so we can write this benchmark in much the same way as we could write our last benchmark. It's just going to be the maximum overall indices I of I times the valuation of the highest bidder, with the caveat that we're now maximizing only over indices I that are at least 2. Okay, so we're going to sort of rule out the possibility, at least in this benchmark, that we sell to only one person. And again, you should really think of this as sort of, just ruling out some unlikely corner case, not as a serious restriction on the benchmark, because again, the whole point of these digital goods auctions is that we can sell many items. We have zero marginal cost of production. And so in sort of the typical case, you would imagine that the best fixed price for Microsoft Word, for example, wouldn't sell to just one person. It would probably sell to many people, like 100,000 or 1 million people. And so that's the benchmark we're going to try to compete with. Okay, so this is a good time to ask questions about either the setup or the benchmark, because the next thing we're going to do, now that we have a goal, a benchmark that we can define instance by instance that we want to compete with, the next thing we're going to try to do is actually to do it. So are there any questions about either the model or the benchmark before we go and try to solve an auction problem? All right. So maybe here's a first attempt, right? Like, we're given an instance, right, V. We can very easily just compute the revenue of the best fixed price that sells to at least 2 people on our instance. And we could try to charge the fixed price that achieves that, right? Because our benchmark is easy to compute given V, right? We just iterate overall I from 2 to n. We can compute like I times, the value of the ith highest bidder. This will be maximized for some I, and the best fixed price will just be, VI for some I. So we could try to just compute the best fixed price and charge everyone that. But of course, that wouldn't be a dominant strategy truthful mechanism. And again, it's sort of easy to see why, right? Like, this mechanism would be charging everyone the valuation of some bidder I. And so in particular, bidder I would have a strong incentive to reduce their price, right? Because the price that bidder I is being charged here is equal to his bid, and he would typically have some wiggle room to reduce his price a little bit, still corresponding to the profit maximizing pricing, and that would reduce the amount of money that he needed to pay. Okay, so sort of like the naive first attempt of just computing the best fixed price on this instance and charging that fails because that's not a truthful mechanism. And so here's a second attempt that's maybe just a little bit more sophisticated. You could say, okay, I sort of understand why our first naive attempt failed. If I want a truthful mechanism, then it had better be for every bidder I that the amount that I ask them to pay is independent of the valuation they report, because otherwise they're going to report the valuation that minimizes their payment, even if that's not truthful. And so how about I compute maybe a different price for each agent? And what I'm going to do for agent I is I'm just going to look at everyone else. I'm going to look at sort of everyone other than agent I. So I'll look at this instance V minus I, the set of n minus 1 bids resulting from removing agent I. And I will compute the best fixed price on the n minus 1 remaining agents. And whatever that best fixed price is, I'll charge that to agent I. Okay, so I'm still, hopefully getting a pretty good estimate of whatever the best fixed price is for every agent I. I'm going to compute it on almost as large a data set, on a data set of size n minus 1, but I'm computing it in a way that's independent of agent I, and so I'll still get a dominant strategy truthful mechanism. Right. So this, if you've done some machine learning, this kind of looks like leave one out cross validation. I'm going to try to, for every person I remove them from the data set, compute the best fixed price on everyone else, and then charge that to person I. And so this does indeed yield a truthful mechanism, right? Because the price that I charge to you is independent of your reported valuation. It's a function just of everybody else. And so there's no way that you can benefit by deviating. Your price is independent of your report. And so the only question is, is it competitive with our benchmark? And unfortunately, the answer is no, it's not. And again, here's a bad example. So suppose we have 2 kinds of agents. I'll call them low value agents whose valuation is 1, and high value agents whose valuation is 10. Okay? And suppose I have a lot of the low valuation agents. So I've got 90 low value agents, and I've got 10 of the high value agents. And so on this instance, we can go through the exercise of asking, what's our benchmark value? What's the revenue we can obtain with the best fixed price in hindsight? And the answer is we can obtain $100. And there's actually two different ways to obtain $100. I could either charge $1 or I could charge $10. If I charge $1, everybody wants to buy the item. There's 100 people total. They all buy the item. They all pay me $1. I get $100. Or I could charge $10. If I charge $10, only the high value agents want to buy the item, but they each pay me $10 and there's 10 of the high value agents, so I also get $100. Okay, so I can obtain my benchmark with two different pricings, either 1 or 100. But let's look at what this sort of proposed mechanism in attempt 2 would do. Okay, it would charge different prices to the low value and the high value agents. And my claim is it would charge exactly the wrong prices. Okay, so first let's consider what it would do for a low value agent. Right, so what it would do is it would consider the vector of valuations of 99 remaining valuations other than buyer I. And it would, on these, on this smaller instance, this instance of 99 bidders, it would compute the best fixed price. Now, the best fixed price would be unique on this smaller instance, right? Because I could charge $1, everyone would want to buy. But now that wouldn't make me $100. That would only make me $99 because on this smaller instance, there's only 99 bidders. Or I could charge $10. That would still make me $100 because there's still 10 high value agents after I've removed one of the low value agents. And so the benchmark revenue on this smaller instance is still 100, but the best fixed price is now uniquely $10. And so what this mechanism would do is it would charge all of the low value agents $10. And so none of the low value agents would buy the item. Okay. Now what would it do for the high value agents? Well, it would compute the best fixed price on the residual instance that results after I remove one of the high value agents. But again, there's now a unique best fixed price on this residual instance, and it's $1. Because if I charge $1, everyone buys the item. There's 99 people, so that makes me $99. But if I charge $10, only the high value buyers buy the item, and on the residual instance, there's only 9 high value buyers, and so I'd only make $90. And so this mechanism is going to charge $10 to the low value bidders, and it's going to charge $1 to the high value bidders. And so it's only going to get a profit of 10, even though the benchmark we're trying to compete with is 100. So here's an instance on which we do a factor of 10 worse in terms of revenue. And of course, there's nothing special about 10, right? You could modify this instance so that so that our proposed mechanism in attempt 2 does a factor of 100 worse or a factor of 1,000 worse compared to the best, compared to our revenue benchmark. And so our second attempt, at least it was a truthful mechanism, but it doesn't approximate the benchmark to any finite factor that we want to approximate it to. Okay, so we have to be a little bit more clever. And so let's try to build up some tools, and in particular, let's start with an intermediate goal. Rather than solving the problem in one fell swoop, let's see if we can solve some simpler subproblem and reduce to that. So in particular, suppose someone whispered in our ear a target profit R. They said, okay, forget about obtaining the optimal revenue on your instance. I would like you to obtain revenue exactly R. I'd like you to make R dollars. Okay? So with this information, maybe we can design a mechanism that will obtain revenue R if it's possible, if the benchmark that we're trying to compete with is actually R or greater. And if our target profit was unachievable because it's actually bigger than our benchmark, then our mechanism doesn't have to make any money at all. Okay, so this is a substantially weaker goal than the problem that we eventually want to solve. We're not trying to maximize profit on any particular instance. We just have a target profit level R, and we want to design a dominant strategy truthful mechanism that will make R dollars if that's feasible to do. If R happens to be less than the benchmark we're trying to compete with, and if R happened to be too big, then we have no obligation to make any money at all. Okay. And this turns out to be a problem that's not too hard to solve. And here's the definition of a simple mechanism that we're going to show solves this problem. It's called a digital goods profit extractor. And it'll take as input both an instance V and this target level of profit R. And it's going to do the following. Okay. It's just going to find the largest value K, the largest number of bidders K, such that there are K bidders who are each willing to pay at least R over K dollars. Okay. And if there is any such K, it will set the price to be R over K, and it will sell to those K bidders at exactly R over K dollars. Of course, it might be that there is no such K. It might be that for every K, if I look at the Kth highest bidder, his valuation is less than R over K. In that case, the profit extractor will do nothing, or rather it will set the price to be infinity, and it won't sell the item to anybody, and it'll make $0. Okay, yeah, and the claim is that this simple mechanism is going to solve the sort of simple restricted problem that we set out here. That first, it's dominant strategy truthful, and second, that it'll make profit of R when R is an achievable target, when R is less than the benchmark we're trying to compete with. So we're going to prove some stuff about these profit extractors, but before we do, are there any questions about them? They have a pretty concise definition right here, but do we understand what they do, like as an algorithm? Right, they're going to find the largest number of bidders K, such that the top K bidders each have a willingness to pay that is at least R over K, and it will then set the price at R over K. Okay, so let's try to figure out some properties of these profit extractors, which we're going to find to be useful subroutines. So the first claim is that these profit extractors are actually dominant strategy truthful mechanisms. And let's try to think about why that is, because it's like not totally obvious that they're dominant strategy truthful from the description we've given here. Like, these things don't look like, at least verbatim, they don't look like, ascending price auctions or anything that we're sort of used to thinking about. But it turns out there's another equivalent way to view profit extractors as implementing some kind of ascending price auction, and viewed in this alternative way, it's actually pretty clear that they're dominant strategy truthful. Okay, so observe that what the profit extractor is doing, which recall is it's finding the largest value K, such that there are K bidders who each have a willingness to pay of R over K, can equivalently be implemented as the following iterative process. Okay, we will start with K as large as it can possibly be. K will be N, the number of bidders. And we will iteratively, at our current optimistic guess for what K might be, offer our best possible price of R over K, which is initially R over N, so the cheapest possible price we will ever offer in this process. Okay, so we'll start with K equals N. We'll offer everyone a price of R over N. And now we'll look around the room and we'll say, okay, does anybody reject this offer? Is there anybody who doesn't want to buy the item at a price of R over N? And maybe there is. Maybe there's someone who's going to reject this offer. So if someone rejects this offer, note, by the way, that this means that the Kth highest bidder must have valuation that's less than R over K. And if there is such a person, we'll remove them from the auction. Okay, so as soon as someone rejects the offer, they get removed from the auction. And then we'll just repeat. We just removed someone from the auction, so now there's K minus 1 people remaining in the auction, so we'll decrement K. K is now K minus 1, and we'll repeat the offer. We'll say, okay, among the people remaining, would anyone like to turn down the offer of buying the item at R over K dollars, or do we all want to accept it? Remember now, K is smaller, so we are making an offer of a higher price to a smaller number of bidders. This is now a higher offer because we've made the denominator a little bit smaller, but we're making the offer to a smaller number of bidders because we kicked out the person who rejected our last offer. And we keep doing this. We keep sort of kicking people out who reject the offer and increasing the offer value until possibly we get to a point where all K of the remaining bidders accept the offer. Okay? And if you just think about this, right, like this is exactly the same, this is implementing exactly the same rule as we defined on the last slide when we defined profit extractors. It's finding the largest value K such that the top K bidders are willing to pay R over K, because we tried this at all larger values of K, and we found at all larger values of K that there was at least one bidder who wasn't willing to pay R over K dollars. Okay, and so this is an equivalent description of what the profit extractor is doing. And it's easier to see with this description why truthful bidding is a dominant strategy. Because think about it when posed as this dynamic process. Note that, what are you going to do standing around in this auction, right? At every round, you can like accept or reject, but like really you only have one action you can take, which is to decide what round to reject the offer, right? Because as soon as you reject the offer, you're out of the game. As soon as you reject the offer, you can never win in any future round. And so you should never reject an offer that is, you should never reject an offer for a price that's less than your true value, right? That's a dominated strategy, because if you reject the offer, you're never going to get another chance to win, so you're definitely not going to win the auction. If you accept the offer, you're still going to have the opportunity to reject the offer later. And so there might be futures in which you win at a price you were willing to pay. And so there's never any reason to prematurely reject the offer, which is just to say that reporting a value that is less than your true value is a dominated strategy. On the other hand, it's also a dominated strategy to accept any offers that are above your true value, or equivalently, it's a dominated strategy to report any value that's above your true value. And that's because the prices only go up in this process, right? Like, it's not that you would want to accept an offer now in the hopes of getting a better offer later. Like, if you accept the offer now, first of all, there's some chance, if everyone else also accepts, that you will have to buy the item at this price, which is already higher than your valuation. You wouldn't want to do that. And it's only going to get worse from here on out, because the price is only going up as we run this auction. So it's also a dominated strategy to accept offers that are higher than your value in this iterative process, or equivalently, it's a dominated strategy to report to the static process a valuation that's higher than your true valuation. And so it's a dominant strategy for every bidder to report their true valuation, and we get what we wanted, which is that the profit extractor is in fact dominant strategy incentive compatible. Okay. So it's dominant strategy incentive compatible. I claim it also solves the sort of simple subproblem we set out for ourselves, not the full problem we want to solve of maximizing revenue instance by instance, but it sets out the problem that it solves the problem that it set out to solve on its own terms, which is to say that on any instance for which the benchmark value, the best fixed price, actually made more than R dollars, the profit extractor will make R dollars. And on any instance for which the best fixed price makes money that's less than R, the profit extractor will make no money. And that's the property that we sort of wanted in this restricted problem, that if we were lucky enough to set an attainable revenue target, that this would exactly hit the revenue target. And so let's observe why that is. So first, let's just sort of write down what our revenue target is, right? Remember, we had a pretty simple expression for the revenue of the best fixed price, right? And it was just the product for some k of k times the value of the kth highest bidder, right? Because the best fixed price in hindsight we established was going to be equal to the valuation of one of the bidders. And if it's equal to the valuation of the kth highest bidder, then we sell to k people. So whatever this benchmark is, we can write it as a product of k times the value of the kth highest bidder for some k between 2 and n. Or equivalently, right, if you tell me that this benchmark value is bigger than r, then I can divide through by k and just learn that the value of the kth highest bidder had better be at least r over k, right? If there's some k such that k times v of k is greater than r, equivalently, v of k, the value of the kth highest bidder, has to be bigger than r over k. And so we've established, right, that the profit extractor will sell to somebody, right? Because the only, it tries to find the largest value of k such that there are k people willing to pay r over k, right? So, the only concern is that there is no value of k such that the value of the kth highest bidder is bigger than r over k, but because of our assumption that the benchmark value is greater than r, we know that there is some such value of k. Now, the profit extractor might find some larger value of k, right? The profit extractor might not find the k that maximizes k times v of k, because the profit extractor is not trying to find the optimal revenue on this instance. It's only trying to make r dollars. R might be substantially suboptimal. But we know that it'll find some k prime that is bigger than k, such that the value of the k prime highest bidder is at least r over k prime, right? Because it's finding the largest such k prime, and we know that k prime equals k is a feasible selection. So we don't know that it'll pick k prime, but we know that it'll sell to some number of bidders. Oh, sorry, we don't know that it'll pick the same k as the benchmark, but we know that it'll sell to some larger number of bidders k prime. And it really doesn't matter how many bidders it sells to if our goal is only to hit this target revenue r and not to maximize revenue on the instance, right? Because we only need to make r dollars, and no matter what k prime we pick, well, we're going to sell to k prime people at a price of r over k prime, and so we'll make exactly r dollars. Okay. And of course, in the other direction, if our revenue target was unrealistically large, if our revenue target was actually higher than our benchmark value, well, writing out the definition of our benchmark, we see that r is bigger than k times v of k for all possible k, which is just the same as saying that for all possible k, v of k is less than r of k. V of k is less than r divided by k. Okay? Or equivalently, it's not possible to find any k such that the top k highest bidders are willing to pay r over k dollars. And so the mechanism won't find any such k because no such k exists. It'll halt without selling to anybody, and it won't make any money. Okay? So this doesn't give us a full solution to the revenue maximization problem for digital goods auctions, but it has solved the simpler subproblem. If somehow we are able to guess correctly a value of r that is sort of achievable, then this profit extractor gives us a dominant strategy truthful mechanism that is able to make r dollars for us. So this is a useful tool. It's not the solution for the ultimate problem we want, but it's some like useful subroutine. And the question is, can we make use of it? Can we somehow reduce the problem we want to solve to the simpler problem that we already know how to solve? So let's think about that. Like what do we know how to do? Well, we know how to obtain revenue r, or we know how to obtain revenue r if someone whispers to us that it is possible to obtain revenue r with a fixed price. right? So like, there's this question of how we come up with a feasible R that is close to the benchmark. But if someone were to sort of whisper in our ear, you know, that the optimal benchmark value was $1 million, and we then ran our mechanism with a value of R that was, you know, $900,999, then we would have successfully approximated our revenue benchmark. So the question is, can we do something that replaces this need for an oracle to whisper in our ear the best value of R? And said another way, what we've done is we've reduced our problem to a statistical estimation problem. Okay, we've reduced our problem to finding a good estimate of the true optimal revenue value R star. You know, if we can somehow estimate our benchmark value, then we can plug that into this mechanism and get, you know, achieve a target revenue that's equal to our estimate. And so we've reduced this mechanism design problem to a statistical estimation problem, with an important caveat, right? Like, remember, for truthfulness, it's important that the price that I offer to every person is independent of their bid. And so in particular, when we argued that the profit extractor was a dominant strategy truthful mechanism, we needed that R, this revenue target that parameterized the mechanism, was defined independently of the bids of the bidders that we were running the profit extractor on. So if we want to come up with a truthful mechanism, we need to come up with some estimate for our profit benchmark that is both a good estimate, but that is obtained independently of the bids of the bidders that we're going to run the mechanism on. So that's sort of our challenge, to try to do both of these at the same time. And the idea is pretty simple, and we're going to call this the random sampling auction. The idea is to try to take a random sample of the bidders to estimate R star. We're going to try to take a random sample of the bidders to try to come up with a good estimate for the revenue that's obtainable by the best fixed price. And then we're not going to run an auction. We're not going to run the profit extractor with this estimate R star on the same bidders that we use to estimate this quantity. That wouldn't be a truthful auction. Instead, we're going to run the profit extractor with this estimate R star on the other bidders, on the bidders we didn't use to estimate R star. And so the hope is that, you know, if we take a large random sample, then we'll have a good estimate for what the best fixed price is in hindsight on our full population. And we'll still have a truthful mechanism because we are going to use a different set of bidders to make the estimate than we will use to actually run the auction. And so here's the random sampling auction. Okay. So we start with some arbitrary collection of n agents. Each one has some arbitrary valuation v. We're assuming nothing about where these valuations are coming from. There's no distribution here. And the first thing we're going to do is we are going to randomly partition the agents into two sets that I'll call S prime or S double prime. Okay, so for every agent, we're going to flip a coin, and if the coin comes up heads, they're put in set S prime. If the coin comes up tails, they're put in set S double prime. Okay, so we just independently randomly partition the agents. Okay, and now I'm going to look at set S prime, and I'm going to compute the revenue that is obtainable by the best fixed price in hindsight that sells to at least two bidders. I'll just compute our benchmark value on set S prime. That's easy to do. Okay, let's call that number R prime. Similarly, I'm going to compute the benchmark value, the revenue obtainable by the best fixed price in hindsight that sells to at least two bidders. I'm going to compute that on set S double prime as well, and I'll call that R double prime. Okay? And then here's the trick. I'm going to run two copies of the profit extractor, one on S prime and one on S double prime. But the copy of the profit extractor I run on S double prime is going to use the profit estimate that I obtained from S prime. And the copy of the profit extractor I run on S prime is going to use the payment estimate that I made from S double prime. Okay, so I split my set of bidders in two at random. On each of them, I just computed exactly the revenue obtainable by the best fixed price. And then I ran profit extractors on S and S prime, but I swapped my estimates so that the estimate I'm using on each set was computed independently of the bids of the people in that set. And that's how I'm going to get dominant strategy truthfulness. Okay. So let's see, we've got a question. How do we perform the calculation without having to offer people goods? Well, remember, this is an auction. So people are reporting their valuations. And if we can argue that this is a dominant strategy truthful auction, they're going to report correctly, like what their real valuations are. So the input to this thing is a vector of valuations. And so we can just compute, right, for every possible fixed price. And remember, there's only n of these we have to consider, right? We only have to consider the valuations that are actually submitted as our candidate fixed prices. For each of them, we can just compute what's the profit we would obtain at that price. And so it's, just n computations. Does that make sense? Like, we're back in the auction setting here. No, so we'll talk next lecture about how to, try to do some of the same things with item pricings in a prior free setting, but in this lecture, we're still talking about auctions. Everyone shows up at once, and what it means to prove that, for example, the profit extractor is dominant strategy truthful is that people are incentivized to report their true valuations. Does that make sense? Great. Any other questions about the mechanism? So it's, like a little bit clever, right? It's sort of doing some statistical estimation. It's randomly partitioning the data set into two parts. On each part, it's independently estimating the profit of the best fixed price. And then it's running this profit extractor on each part, but with different estimates of the best fixed price. Crucially, on each part, our estimate of the optimal revenue is computed independently of the bidders in that part. That's what's going to get truthfulness for us. Okay. So we can immediately observe that this mechanism is dominant strategy truthful because we already proved that the profit extractor is dominant strategy truthful whenever it's parameterized with a value R that is independent of the bids that the bidders make. And that was sort of the cleverness in this random sampling auction. We run two profit extractors here. And for both of them, the revenue target R was computed independently of the bidders in that part of the auction. It was computed as a function of the bidders in the other part of the auction. So the random sampling auction is indeed dominant strategy truthful. Okay. Another simple observation. The revenue that we obtain from the random sampling auction is at least the minimum of R prime and R double prime. Remember, R prime is the best revenue obtainable by a fixed price on set S prime. R double prime is the best revenue obtainable by a fixed price on set S double prime. And the claim is we get at least the minimum of whatever these two are. And again, this is sort of obvious because either R prime is greater than or equal to R double prime, or R double prime is greater than or equal to R prime, or possibly both, right? And so at least one copy of this profit extractor is going to succeed, right? Like, remember the guarantee of the profit extractor, it succeeds whenever its target is smaller than the benchmark value on the instance it's run on. And so, like, either the target in set 1 is bigger than the target in set 2, or vice versa. It can't both be false. So at least one copy of the profit extractor is going to succeed, and maybe both of them will. And so we are going to get revenue that's at least the minimum of the benchmark value on set 1 and set 2. And so this reduces our problem to analyzing the minimum of the revenue obtainable by a fixed price on set 1 and set 2 as a function of the revenue obtainable on the entire instance. Okay. And so let's think about this. And in order to think about it, I want to think about sort of a, like purely combinatorial question that'll be directly relevant to the analysis of this auction. So suppose I flip K coins, right? K like fair coins, right? So when I flip a coin, half the time it's heads, half the time it's tails. And suppose I flip K coins and at least 2 of them, that K is at least 2. Okay. Then I claim that if I look at the expected number, the expected value of the minimum of the number of heads I've seen or the number of tails I've seen, that's at least K over 4. Okay, so let's just like make sure we understand this quantity we're making claims about. I'm going to flip K coins. Some of them will come up heads. Some of them will come up tails. I'm going to count how many heads there are. I'm going to count how many tails there are. I'm going to take the smaller of those 2 numbers, and I'll take the expectation of this value. The claim is that's at least K over 4. And really, this is sort of pessimistic. Like, it'll be something like this if I'm really only flipping 2 coins. Of course, as I start flipping more and more coins, the quantity on the right-hand side should converge to something like K over 2. Okay, so let's prove this sort of simple fact. Okay, so first we'll just define some notation. So we're interested in the expected value of the minimum of the number of heads and the number of tails when I flip K coins. Let's just define this value for any I. Okay, so let's let mi be the quantity we care about when we flip I coins. Mi is just the expected value of the minimum of the number of heads and the number of tails when I flip I coins. So the thing we want to prove a theorem about is mk. And we can figure out directly what mi is for some small values of I. So for example, if I flip 1 coin, then, well, it'll either be heads or it'll be tails, right? So the number of heads will be 1 or the number of tails will be 1, but the other one will have to be 0 because I only flipped 1 coin. So if I flipped 1 coin, then the minimum of the number of heads and the number of tails has to be 0. So m1 is 0. How about if I flip 2 coins? Well, there's 4 things that can happen if I flip 2 coins. I might get a heads tails or I might get a tails heads. In either of those 2 cases, the number of heads is 1 and the number of tails is 1, so the minimum is also 1. Or I could get 2 heads in a row, or I could get 2 tails in a row. In either of those cases, the minimum of the number of heads and the number of tails is 0. So half the time the minimum is 1, half the time the minimum is 0, and so we can directly see that m2 is 1/2. And so more generally, I can define xi to be the difference between mi and mi minus 1. Right? It's the expected increase that I expect. There's the expected increase in this minimum count after I flip the ith coin. Okay, these mi's are like monotonically increasing quantities, and xi is just the amount that I expect mi to be bigger than mi minus 1, or it's the expected contribution of the ith coin to this value, to the minimum of the number of heads and the number of tails. And by linearity of expectation, right? If I want to know, well, what's the expected number of, what's the expected value of the minimum of the number of heads and the number of tails I've seen after K coin flips, this is just equal to the sum over all of the coin flips I make from 1 to K of the expected increase in this value after the ith coin flip. Okay, so, it's the thing on the left that we are trying to prove a lemma about, trying to prove a theorem about, but it's equal to the thing on the right, which is just a sum. And so if we can compute values for these xi's, then we're going to be done. Okay. And there's going to be two cases here depending on whether I is even or I is odd. So I know some of you in this class are math majors. I don't know how many people have taken a number theory course, but if you have taken a number theory course, here's something you would have learned in the first or second semester, which is that if I is an even number, then I minus 1 must be an odd number. And so in the case in which I is even, I know that I minus 1 is odd. And so in particular, like if after I minus 1 coin flips, it cannot possibly be that the number of heads was equal to the number of tails, because I can't divide an odd number exactly in half while having both halves be integer. And so in the case when I is even, it must have been that before the ith coin flip, the number of heads was not equal to the number of tails, and one of these two counts was therefore smaller than the other one. And in this case, we can therefore see that xi is exactly 1/2, right? Because we're going to increase the minimum exactly when our coin flip comes up with the same sign, heads or tails, as whatever is currently the minimum of those two counts. They're not both equal, so increasing the minimum value will increase the value of the minimum. Okay, and it's a fair coin flip, so I will contribute to the smaller of these two quantities with probability exactly 1/2. On the other hand, it might be that if I is odd, that I have no contribution at all, right? It could be that if I is odd, well, then I minus 1 is even, and so it could be that the number of heads was exactly equal to the number of tails prior to the ith coin flip. If that was the case, then no matter how my ith coin flip comes up, it's not going to increase the minimum value. Okay, so usually that won't happen. So if we wanted to be more clever, we could say something more nuanced here. But for our purposes, it's going to be enough to observe that when I is odd, at least xi is like non-negative. I can never like decrease the minimum value. I can only increase it. Maybe I won't increase it at all when I is odd. That'll be okay because I know I'm increasing it when I is even, and I is going to be even half the time. Okay, so we can say that m of k, the expected value of the minimum of the number of heads and tails after k coin flips, well, we know it's the sum from I equals 1 to k of the marginal contribution of the kth coin flip, and that's going to be at least k over 4, because half the time I was even, and whenever I was even, we know we contributed exactly 1/2 to this. And we were sort of lazy, and we didn't take into account the contributions when m was odd, but that's going to be good enough for us. Okay, there's a caveat having to do with floors, but actually it's okay. Okay. And so this brings us to our theorem, that the random sampling auction always, on every instance, will obtain within a factor of 4 of the revenue of the best fixed price in hindsight. And remember, this means that the random sampling auction, without needing, if the values were drawn from a distribution, the random sampling auction will always obtain at least a 4 approximation to the revenue of the optimal auction that had the advantage of knowing what the distribution was, even though the random sampling auction didn't need to know what that distribution was. Okay, so sort of, we got this, on the one hand, we're not achieving our benchmark, we're only achieving within a factor of 4 of it. But on the other hand, we're not assuming anything, so we're really getting an instance by instance bound that's much stronger than an average case bound. And if we are in a world where values are drawn from distributions, we're doing it in a way that works even though we don't know what the distribution is. Okay, and so let's prove that. And so remember what we've already shown, right? The revenue of our random sampling auction is at least the revenue obtainable, or it's at least the minimum revenue obtainable on either set S prime or set S double prime, these two random partitions that we made at step 1 of the random sampling auction. Well, we made those partitions randomly, so our expected revenue is at least the expected value over the randomness of this partition of the minimum of R prime and R double prime. Okay, now there's this benchmark we're trying to compete with, right? The revenue of the best fixed price, which we know can be written in the form k times p for some k greater than 2, because our benchmark is only for prices that sell to at least 2 people, and for some price p. There's a question: does the fact that we're able to achieve a bound despite having very little information actually indicate that this is a good strategy, or does it just indicate that a 4 approximation is not a strong benchmark? Let me get back to that on the last slide, because I'll discuss the 4 approximation. But briefly, it is a good benchmark because it is only a stronger benchmark than the Bayes optimal benchmark. That is, because we know for random sampling auctions that if we knew the distribution from which bidders were drawn, the optimal auction would have the form of selling to everybody at the same fixed price. And so because we're competitive with that benchmark, that in particular means we're competitive with this optimal class of auctions that needs more information than we have. Now there's this other question of whether a 4 approximation is good enough. Let me get to that in the slide. But okay, so we know that like our benchmark can be written as k times p, because we're gonna sell at some price p to k people. So let's think about these k people. Okay, when we randomly split people into these 2 sets, S prime and S double prime, these k people that we would sell to at the optimal price p will also be split between them. Okay, so let's let k prime be the number of these people who end up in set S prime, and let's let k double prime be the number of these people who end up in set S double prime. And observe that whatever the optimal revenue obtainable is on set S prime, it's at least k prime times p, because we could sell to these k prime people at price p. Maybe the optimal revenue is better. Maybe on this subset, we're actually better off selling at some other price, but at least we know how to obtain revenue k prime times p on S prime. And similarly, the optimal revenue on set S double prime is at least k double prime times p. And so, we're interested in the ratio of the revenue that we obtain to our benchmark, right? We want to show that this ratio is at least a quarter. And so we can bound this ratio. On the one hand, our revenue is at least the revenue of, is at least the minimum revenue obtainable either on set S prime or on set S double prime. On the other hand, the benchmark value we know can be written as k times p. And we know that R prime is at least k prime times p, and R double prime is at least k double prime times p. And so these p's can cancel out in the numerator and the denominator. And so this ratio of our revenue to the revenue of the best fixed price in hindsight, our benchmark, can be expressed exactly as this fact about coin flips we just proved, right? Because what are k prime, and k double prime? Well, we flipped k coins to figure out whether the k winners under the best fixed price in our benchmark would be split into set S prime or S double prime. If they came up heads, they went into set S prime. If they came up tails, they went into set S double prime. And so our revenue is exactly equal to the ratio of the minimum of the number of heads and the number of tails we get when we flip k coins to k. And we proved that that was at least a quarter. And so that's it. And so let's briefly reflect on, is this a good result or a bad result? So on the one hand, it's a great result, right? Like we can approximate the revenue of the Bayesian optimal auction without knowing D. In fact, we do this not just in expectation, but we really do it instance by instance. And we didn't even need to assume, not only do we not need to assume that we know D, we don't need to assume that the values were drawn from a distribution at all. Because we're not giving an average case guarantee. We're giving a instance by instance guarantee, which is substantially stronger. So that's the good side. That's the good news. On the other hand, we didn't get like a great approximation. We got within a factor of 4. And so, it's nice to say that we're competitive with optimal. On the other hand, telling your boss that, you got 25% of the revenue that might be obtainable might not make him super happy. But the reason why we only got a 4 approximation is really because we sort of proved the theorem that we proved a theorem that worked even when the best fixed price in hindsight sold to only 2 people, right? Like we only ruled out this case where the best fixed price sells to 1 person because in that case we couldn't be competitive at all. But really, like, if we're selling software, say, we really sort of expect that we're going to sell to a lot more than 2 people. And the problem becomes easier as you intend to sell to more and more people. So, you could think about it, but like, once you've seen the random sampling auction, it's actually not too hard to use the same ideas to generalize this to get a increasingly good approximation, like a 1 plus epsilon approximation for an arbitrarily small epsilon, to the benchmark that corresponds to the best fixed price that sells not to at least 2 people, but to at least k people as k becomes large. So the better the approximation you want, the bigger you need k to be, but that's not so unreasonable in a large market. All right, so I'm gonna stop the recording now, but I'll stick around for a minute or 2 to ask questions.